All right, everybody, we're going to talk about the rational roots theorem in this video. This is the culmination of everything that we've been talking about so far. So we now have a polynomial. This one happens to be a quartic, degree 4. No hints, and we're asked to solve it. We're asked to find all of the solutions. And at this point, outside of guessing, there's not really much that we can do. I know that if it's a degree 4, we're expecting 4 solutions. But those solutions could be made up of nice, neat numbers like 2 and -5. It could be made up of fractions. It could be made up of numbers that have square roots in them, irrational numbers. And it could be made up of imaginary numbers or complex numbers. So what the rational roots theorem aims to do, and notice the word rational, it helps us narrow down at least the rational roots. And we're going to be able to come up with a smaller list than all of the numbers from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and up. Also the negatives, also the fractions. So here's what the rational roots theorem says. It says if our polynomial equation has integral coefficients, that means the integers, which means no fractions, no fractions, no roots, no i's. So if we have basically a pretty fraction, if it has the root, it will have the root p over q, where p and q are relatively prime integers, and then p must be a factor of the constant term of the, and k must be a factor of the, actually, I think the k should probably, that's probably a typo, that should probably be a q. And the idea is, this is relatively complicated just to read, to diagnose and be able to use near impossible without a little explanation. From a different text, the rational root theorem in the yellow box here. If we have a nice, neat polynomial with, again, those integer coefficients, then every rational solution has the form p over q, where p represents a factor of the constant and q represents the factor of the leading coefficient. That is a little bit better. We're going to learn a process that will remove the need to analyze and understand and frankly translate what this all means. And we'll do that by completing our first example. Okay, so if this is our example, again, we're still expecting 4 solutions. Here's how we're going to use the rational roots theorem. All right, step 1 says to list all the factors of the constant term. The constant term is the 4, and yes, I guess technically it's a -4. We're going to be able to say that that number is going to represent, or its factors are going to represent the p's. Okay, and that means that we need to think of all the things that 4 can factor by. So I can factor every number by 1. I can also divide 4 by 2 evenly. I cannot divide 4 by 3, but 4 will divide by itself, and obviously we're not going to be able to divide by anything larger. Okay, now we can ignore the negative part of the 4 because you'll see in a few moments that we're going to use both positive and negative values anyway. Okay, we also want to list the factors of the leading term, which is 3. So the value 3 is going to give me what we'll call the q's. Since 3 is prime, its only factors are 1 and 3, but if we had larger numbers, we may have to make this list a little bit longer. Okay, now step 2 asks us to list all the possible combinations where we take these values in purple and blue and form a fraction out of them. And then, of course, as it says in the box, they can be both positive and negative. So if I make the fractions, which we'll call p over q, I really need to pair each of the purple ones up with each of the blue ones. I usually think about holding one of them constant and then alternating through the others. So what I mean by that is keep the value of q at 1 and alternate through the 1 and the 2 and the 4 that make up my p's. And then I'll change the q to a 3 and do the same thing. And this is all the ways that we can pair the numbers 1, 2, 4 in the numerator and the numbers 1 and 3 in the denominator. And what we'll do is then we'll reduce those. So 1 over 1 is just 1, And like I said, they can both be positive or negative, so I'll put a plus or minus in front of them. This represents both the number positive 1 and negative 1. 2 over 1 is 2, so plus or minus 2. 4 over 1 is 4. I've got 1/3. I've got 2/3. And I've got 4/3. Now, sometimes they reduce. In this problem, none of them reduced, but you will find from time to time, you may have like a 2 over 1 and then a 4 over 2. Those are the same number. You can kind of cross them out. Now, what I usually think about this moment is all those red numbers are my candidates. They're suspects for possibly have committing the crime of being a solution to our polynomial equation. Now, there's no guarantee that the answer is in there, but it usually is, especially if I'm going to be giving these problems for you to work on. But these are the only ones that are possible as solutions that are also rational. There are still other types of answers that we've seen. They could have roots in them. They could have i's in them. But if it's going to be a rational number and a solution, it's got to be in this list. All right, now for the next step, we are going to use the remainder theorem. Almost everybody uses synthetic division here, although you do have a few options, to test these. If I continue the analogy that these are suspects, we got to call them in for questioning. So we will actually test to see if we can get a remainder 0 when we divide that original polynomial by, x plus 1, or we synthetically divide by negative 1. So let's write out the terms of my polynomial as 3, 4, negative 1, positive 4, and negative 4. Hoping again that this value down here is a 0. If we get that, then we've found one of our answers because it divides each. So I'll grab my first value to test. Let's actually test the value positive 1. It should be easy to run through. If I do that, bring down the 3, multiply by 1, add down, multiply by 1, and add, and multiply, and add, and multiply, you can see that we are not going to get a 0 down here. So the number 1 is not a solution because remainder was not 0. And we'll do all this again, either by just writing out a new synthetic division problem, or like I'm going to erase it. Now let's test negative 1. And we'll follow the same process. Bring down the 3, multiply by negative 1 and add, and multiply by negative 1 and add, and multiply by negative 1 and add. And again, we are not going to get a 0. So negative 1 is not a solution either, for the same reason. And at some point, we realize that we're going to have to test through these a few different ways. And as we test them and we find that they don't work, it makes sense to cross them off. They are no longer suspects because we have, for sure, they have an alibi if the metaphor can get that convoluted. So we'll keep testing and continue crossing values off. And then finally we find that negative 2 is a solution. And what's nice about that is we also, in addition to knowing now that one of our answers is negative 2, we also have a quotient where the other 3 answers are remaining. So I don't know if we're going to jump to this just yet, but we could take those values and come up with a polynomial like 3x now cubed, reducing the power of 4 by 1, minus 2x squared plus 3x minus 2. Now, at any point, if you end up with a polynomial that is factorable, actually, this polynomial is factorable, you can tackle it. You can jump into some grouping here and come up with the remaining few factors that we have. However, what if this polynomial was not factorable? What we would do is, instead of making it into the polynomial, we would do, again, some more back-to-back synthetic division using this new row of 3, negative 2, 3, and negative 2. Again, hoping that the end result is a remainder of 0. And you can actually test negative 2 again. There's a possibility we get a double 0. Let's go ahead and do that. 19. Okay, it's not going to give us a 0. So now we can actually cross out the negative 2. We got it as one of our answers. but it's not going to give us a second -2. And we can continue to go through this list. We can test 4 and -4 and 1/3. Let's actually practice with a fraction. 1/3. So we'll bring down the 3. Multiply by 1/3, which gives me a 1. Add together. Gives me a -1. That's a -1/3. 3 is 9/3. 9/3 minus 1/3 is 8/3, and if I multiply it by 1/3 again, I get 8/9. Definitely not 0 here. So that one won't work either. And you could kind of trust me on this. I've done the work ahead of time. The next number in that list, if we are going in order, that does in fact work, is going to be a positive 2/3. And just to make sure that it works, bring down the 3, multiply by 2/3. Add them together, multiply again by 2/3 is 0, and 3 times 2/3 gives me 2. There's that 0 that I want. So I have another root. And the reason that we kind of do this synthetic division step multiple times is because at some point we have reduced the degree to a point where we get a quadratic. So again, we said we started out with an x to the 4th. We're expecting 4 solutions. Once we divide the first time, this 3 would represent an x cubed. And as we divide a second time by the 2/3, this 3 now represents an x squared. So we really have here 3x squared, 0x, and then plus 3. Which is good for us because the last step that we have is to divide, factor, or use any other techniques we have for solving quadratics to get the last ones. And I know that if I have an x squared, then I'm going to be able to at least do the quadratic formula. So I'll kind of tuck that step up here. There we go. And I will say that now we can, try to factor the 3x squared plus 3, jump to the quadratic formula if we want, but it would look like, let's actually factor it. I got 3 times x squared plus 1. And because this is a quadratic binomial, we should be able to use the square root method. So x squared plus 1 equals 0, or x squared is equal to -1, or x equals plus or minus the square root of -1, which is plus or minus I. And there we have it. These are the 4 solutions to our equation. We have plus or minus I, -2, and 2/3. And it validates the 4 solutions we were expecting, and we didn't need any hints, and all of the individual steps, like I've been saying for a few lessons now, individual steps easily able to be done. Now we're trying to string them together into a procedure that is digestible. All right, then, as one small sidebar, if you're willing to do a little bit of work at the beginning, there is one sort of like cheat code that may or may not be helpful. You can use Descartes' rule of signs, and that may tell you that, for example, there are no positive real solutions, or there are no negatives, or you have an odd number or an even number. Here's what I mean. For this problem, which is already done, we lost our opportunity to use the cheat code, but 3x to the 4th, 4x cubed, minus x squared, plus 4x, minus 4 is the polynomial. I'm going to put equals to 0 anyway. And if this is my p of x, this has 1, 2, 3 variations in sign. That means that we're either going to get 3 or 1 positive real solutions. If I were to take that polynomial and decide the signs of p of -x, recall that all the even-powered terms stay the same sign and the odd-powered terms become opposite sign. So what's most important, not necessarily the numbers, but the fact that the 4th degree term, if I plug in -1, or -x I should say, is positive. The cubic term is going to be negative, it's going to switch. The x squared term is going to stay the same. the linear term, oh no, the linear term is going to change. And then the constant term is going to stay the same. So this one only has one variation in sign, and that means it's going to have one negative real solution. And like I said, this may or may not work because real solutions include all the square root ones. Irrational numbers are real too. But this should, somewhat validate what we got. And if we look at our solutions, then we actually have one negative. Well, there it is. That was a -2. We have one positive real number, and then two complex numbers in our I and our I, negative I. So how could this have helped us in this problem? Well, I suppose if we had done Descartes' rule of signs and realized that we're only going to get one negative, as soon as I found that -2, which we actually did do first, I would stop testing negative numbers. All the numbers in my list that are negative can no longer be solutions according to Descartes' rule, because we found the one and only negative real solution. All right, now let's take a few minutes to just work through one start to finish, try to use Descartes' rule to help us out a little bit, and remove the teaching aspect. This is now in practice mode. We're going to hopefully see all the same steps, let them sink in, but you can, of course, reference the step-by-step guide or the theorem itself if you need to. And actually, with this example, the first thing that is wrong is that we need this to be equal to 0. I don't need to go through that process with you at this point, but keep in mind that if it's messy like this, we're going to get one side equal to 0. Okay, so take a moment to double check that if you move all the terms to the left side, you get a positive 2x cubed, negative 11x squared plus 6x minus 6, and if not, see what happened. From here, we're going to use the rational roots theorem to come up with our potential values. The value of 6 makes up my p's, and the factors of 6 are 1, 2, 3, and 6. And the factors of q are just 1 and 2. They come from the value, the coefficient of the leading term. So my list of p over q's are going to be represented by a bunch of fractions with pluses or minuses. And I could take a moment to set up 8 fractions with the plus or minus in them because I'm expecting that many. If I have 4 values for p and 2 values for q, well, then 4 times 2 is 8. I'm expecting 8 combinations. And I'll do it the same way I did before. I'm going to leave the denominator as a 1 and kind of cycle through my values of p until I exhaust all 4 of them. And then I'll change the value of the denominator to 2 and cycle again through 1, 2, 3, and 6 as values for q. As values for p. And if we reduce these, we have plus or minus 1, plus or minus 2, plus or minus 3, positive or negative 6, positive or negative 1/2. Aha! We have a plus or minus 2 over 2. I'm going to cross that out because we already have a 1. I have a plus or minus 3/2. And again, 6 over 2 can be reduced because we already have a value of 3 in our list. At this point, we have 2, 4, 6, 8, 10, 12 different suspects, 12 different values to check using synthetic division. Let's see if we can do anything about that list. I'm going to use Descartes. And I'm using this as my p of x, which has a positive, negative, positive, negative. That's 1, 2, 3. So we're expecting 3 or 1 positive real answers. I don't know if that helps us too much, but p of negative x, again, will change the sign of any of the odds. So 2 cubed becomes a negative. The x squared stays a negative. The positive 16x becomes negative, and the negative 6, which is a constant state. We have none. We have no variations in sign here. They're all negative. So this is great. We have 0 negative answers. I can effectively cross out all the negative suspects, the negative potential rational roots. And we're left only now with 6 to check. If we set up our problem using the coefficients 2, negative 11, 16, and negative 6. Hoping to get a 0 here, we can test through a few of these values. Let's do a couple wrong ones just to say that we tried the work. If I try the value positive 1, we don't get a 0. If we try the number positive 2, we do not get a remainder of 0. If we try the number 3, we do not get a remainder of 0. And it does seem like we're testing a lot of values, but each of them are relatively quick to try. I'll skip now to the one that I've worked out ahead of time. The one that finally does work would be the last one that we would test. Unfortunately, 3/2 is one of my solutions. So if I bring down the 2, when I multiply by 3/2, the 2's cancel. I can add 11 and 3 and get a value of negative 8. When I multiply negative 8 times 3/2, they cancel and we're going to get a negative 12. When we add down, we get 4. And then 4 times 3/2 is going to be 6. We finally get that value of 0. So for my solutions, I know I'm going to have a 3/2. I'm expecting 3, so I'll leave room for 2 more. And because now, if this 2 represented x cubed, the 2 represents x squared, if we had tested all those values, we would know that there are none left. We've tested all of them. But we definitely do have a quadratic now. So I'm going to turn 2x squared minus 8x plus 4 into my quadratic that I can hopefully, maybe I can factor it. I've got the quadratic formula. This one I won't be able to take square roots like the last one, but I solve this equation however I need to. And I can, in this case, at least take out a 2. But x squared minus 4x plus 2 is not factorable. So unfortunately, I will have to use the quadratic formula on this. And then because we have a common factor in all 3 of these, remember I usually say all or none. You can cancel if it's all the terms on the top and all the terms on the bottom. We can reduce them all by 2, and that would give us, let's put it up here, 2 plus or minus 1 root 2. Or how about 2 plus root 2 and 2 minus root 2. Those are my last 2 solutions. And there's the big picture version of what we did. For the record, we were expecting to get either 3 or 1 positive real solutions. Actually, all 3 of these numbers as our solutions are positive numbers. Even the 2 minus root 2, that's still on the positive side. So we did get, in fact, 3, and Descartes' rule holds up. But, like most things, this is one of those where it's going to make a lot more sense once you get some practice. So I will end the video now, and we'll work on this in class.